then run into the loo and then I'm ready.
Okay.
I'm just going to turn the laser off. I've got to line it all up again. Yeah?
Yeah. All right.
That's that done. We're on 34 seconds. Right, okay. Let's have a go at looking at today some physics, A-level physics, topic by topic, and what we're going to look at is something about diffraction, we'll look at polarization, and we'll look at interference, and we may get on to look at the double slit experiment. We'll see how we do for time. Right, so we've got a whole series of different bits and pieces to have a look at, and the first one is diffraction, the idea about waves spreading out. If we look at this, then what we've got is a simple idea that I've got a series of waves coming at some sort of barrier, and in this barrier I've got a slit, and this slit we can change in size, and what we see is that we get this wave coming out. I'm drawing this now, so hopefully you can see this when we have a look at this in the ripple tank in a moment. As this gets wider, then the shape's going to change. Well, let's have a look at all of this in action. So I've got set up here my ripple tank, so we can have a look at some waves, and I've got at the top here two little barriers, and I could change the width of this barrier here. We can just about make that out. Paul's going to raise the camera slightly so that you can see this small gap here. Now, connected to this I've got an oscillator. Let's make this work, and I'll just need to kick start it, and let's see what we can see underneath. So we're going to move the camera again, and hopefully we can see down the bottom here with the little slit we've got, rather than straight waves coming out, we've got curved waves. And I'm now going to open this up just a tad because it makes it easier for you to see, and we can see these waves spreading out, and they are now circular in fashion, and that's quite good. If we could easily measure the wavelength, and here it's not very easy to do because I've set the barrier very close here to the source, and if I were to make it a little bit further, we could actually measure the wavelength, and we'll find the wavelength stayed the same. And we look at the frequency of the waves, and we see that that also stays the same. Let's make this a little wider. Is it getting any better, do you think? Certainly becoming a little bit straighter here, and you can see that if this were sound waves and you were standing just this side of the barrier, a door, a hole, that you would still probably manage to hear your mum calling you saying dinner's ready, because just as light, water, sound does this just the same way. All the waves work in exactly the same way. Let's open this barrier a little bit more. Now, it's not looking quite the same now. The wave's looking a little bit more disruptive, and instead of going through a narrow slit, we're now going through quite a wide slit. And going through this wide slit here, we can see this wave is almost straight here, but it's curving at the edges, and the further we look out, the better we can see these waves are curving. So this size of the slit makes a considerable difference to the wave, and at one point we get the best sort of diffraction occurring, and this seems to be when this gap equals one wavelength. So if I can approximately make this to one wavelength, and it's about right, then we can see that down at the bottom, and Paul scans down, we get probably about the best waves being produced. So this is this idea about diffraction. So when we're looking at diffraction, what we're looking at is simply waves spreading out. Now, can we look at this in other ways? Yeah, sure. We can look at this with light. We can look at this with microwaves. Now, I don't have enough equipment here to do microwaves, but I can certainly do light. And we can look at light being spread out. We're all taught that light travels in straight lines, and we're not used to this idea that light can spread out. But let's see if we can actually do that. And what we need is to bend the light to, if you like, diffract it. And we've got a simple setup we're going to have a look at to see what we can do. What I've got here is a little screen that I've put up, and I've decided to go for one with squares because it's easier to try and see what we've got going on here. So we've got some squares, and down the other end then we've got a laser. Leave it, we'll need it in a minute. So what I'm going to do is I'm going to put my laser on, and if I have my laser on, I'm going to shine that onto my piece of paper. Now, to go with this, I'm going to try and shine this through a small hole. And I've got here a small target, and this is a piece of aluminium foil, and in this aluminium foil I've got either some single holes or some double holes, and we're going to try aiming this through a single hole and see if it works. And this is interesting when we try and get this to work. Right, so let's have a go and see if I can get the laser, which is pointing there, down to here, and you can see here already it makes a fairly big splodge, and Paul will see if he can zoom in on this to show you what I mean. We've just got a splodge, and this laser itself, when it does so, is making sort of little rings. Can you see them on the side? We've got these little rings, and we'll try and accentuate those by trying to fire it through a small hole. So Paul's going to zoom out a little bit, so because we're going to lose the laser now. And what I'm going to do is I'm going to try and adjust the positioning of my laser so that it's going to go through a single hole onto the piece of paper. Having negotiated my way through the camera, I'm then going to try and make a shadow here so you can perhaps see this a little bit easier. And there's Paul zooming in, and we can see now a much better shape that we're getting, these sort of rings formed really going round. The light is just going through a single hole, and it's spreading out, and as it's spreading out it's forming sort of light and dark areas. Let's look at those light and dark areas in more detail. So let's go over and have a look and see what we're going to try and do with this. So we've looked at water going through the ripple tank, and going through the ripple tank we can see diffraction taking place, and we can see that light is also sort of spreading out a little bit. Let's have a look. So in diffraction, the light, just as we've got the waves here on camera, just as we've got the waves here, start spreading out. If we make this wider, then typically the waves are straight for this bit. This is supposed to be the same length, but they then start curving at the edges. So we're getting a peculiar shaped here wave. We find various properties here. So for diffraction, what properties can we say the same? Well, the speed is constant. We can see that the wavelength is constant. We can see the frequency is constant. It's just the shape of the wave, and this is the reason why sound diffracts when it passes through a doorway, allowing you to hear conversations round the corner. Light does the same, but because it's got a much smaller wavelength, it doesn't diffract through such a large gap, and that's why I had to make a pinprick in a piece of aluminium foil to get it to sort of spread out sufficiently. The amount of diffraction then depends on the size of the gap. If the gap is too small, very little wave energy can pass through. If the gap is very large, there's little effect on much of the wave as it passes through. However, when the wavelength matches the gap size, the wave energy is spread out very effectively through the gap to fill the space behind. And this is where we saw it the best in the ripple tank. So if you look at this with sound, for instance, the audible sound range is sort of from a few centimeters to a few meters depending on the frequency. So a doorway is, let's suppose, about a metre wide. If the door is 1 metre wide, and let's suppose we've got a frequency of someone talking to you, let's say about 330 Hertz, which is about the typical average speech frequency for humans, this means the conversation in a room can be heard in a corridor outside, because the wave here is going to spread out. so that if someone is here, they can hear the conversation really quite well. Light, on the other hand, would be something like about 10 to the minus 7 meters in length, and so we're going to get only the slightest change, spreading out of light as it goes through this gap. Diffraction patterns here, when we look with light, showed a central maximum. And then what we saw was an area of darkness, and then another area of maximum darkness, and then another area darkness, and then another area. And what we were seeing probably better here is in certain directions with my laser, because it's only a cheap one, it seems to be better in these areas and not so good in the other ones, so we don't see the circle quite as well. Now let's have a look and see what happens if we take this laser and we put it through a diffraction grating. So let's see if we can set this up. Paul, could you pass me the laser? Alright. I didn't specify in the stand. I apologise for that. The stand now comes with me. Right, let's have a look and see what's going on. Right, what I've got here is my laser, and I've got my ripple tank in the way, but we'll see what's going to happen with that. And there's my laser shining onto this. Now, what I've got here is in my hand a diffraction grating. And if we look at this diffraction grating the other way round, you can just see as I move it, the light's changing. It doesn't look quite clear. This one's 100 lines per millimeter, this one 300, and this one 600. And what I'm going to do is I'm going to put that into the path of the light. So let's see if I can set this up. I did set this experiment up in practice earlier, but of course I ran into a little technical problem called we were going to use the ripple tank as well. Right, okay, I've got my laser set up, I've got my diffraction set up, but it's too high, so let's lower this so it's going to go through this diffraction grating. And I'm going to try and get it reasonably parallel, and let's see what we get. So this is going through 100 dots, 100 lines here, and we can see we've got a central maximum, and then we've got some other dots which are not as bright, and then some more which are not as bright, and some more, and I've got an extra one on that side I haven't got on this side. Just see it here. Now I've set this up on this squared paper, and the reason I've set this up on this squared paper is so that we can see that the distance here between this point and this point is the same distance as that one, and the same distance as this one, and the same distance as that one. We can verify this by getting my ruler out, and my distance here is about 3.25, 3.25, about 3.3 there, 3.3, 3.4. But it's about the same, within the realms of the accuracy of what we've got. So that's going through the first one. This is 100 lines. Now, what's going to happen if we put it through one with, this time, 300? And what we're seeing now is this distance has increased considerably. Paul's just going to zoom in to show us. And now I've really only got 3 dots. If I do move this piece of paper along a little bit, we might see there's an extra one over there. We're getting this spread out. So with 100 lines, it's spreading out so much. With 300 lines, it's spreading out much more. Now, let's bring the laser a little bit closer. What happens when I bring the laser closer? And the answer is no difference. It's the distance between the diffraction grating and the paper that's going to make the difference. Let's look at now going up to 600 dots. And going to 600 dots, it's doubled the distance here. So if we measure this distance between the 2 dots, that is about 21 centimetres. And if I compare that with going with the other one, got it there, I've got this other dot here to this one, about 21 centimetres, and if we halve that distance we can see that we've got here about 10, about just over 10 there. So we are getting within the realms of experimental accuracy here. Diffraction grating spreading out the light, and it's all due to the number of lines that we've got on this diffraction grating. Let's look at this in a little bit more detail. So we've got a diffraction grating here. If I hold it up here to the other camera, we can see this diffraction grating. And what I should be able to do is put it down here, and you can see that basically you can just see through, no problem at all. It's only when I raise this up that we have some interesting artifacts on the light. Let me try and get that going again. and we can see that the light here is being modified and we're getting some sort of spectrum produced here. And we can see that they're a little bit different. The 600 seems to be wider, 300 is better to see here, and the 100 one there giving up virtually a whole spectrum. Right, so diffraction grating then. Diffraction grating, we're getting some sort of pattern produced and we're getting colours going on, and we've got a formula that can help us with this. N lambda equals d sine theta. Here theta is the angle between the original direction of the wave and the direction of the bright spot. If we look at what we're actually achieving in an experiment like this, then what we've got is we've got a central bright spot, and then at a distance we've got some other dots. So if I set here this to 10, then I might get another dot here and another dot there, and probably another dot there. So this is what we're actually seeing here, and we've looked at this and we can see that we've got here something happening. Our basic layout for this experiment is we've got the laser, it's shining on a diffraction grating with either, in this case, 100, 300 or 600 lines per millimeter, and this then goes out onto a screen which is a distance away. If I take my bright spot and we take my next spot here, this is our angle theta that we're talking about. Just try and zoom in for you a little bit. There we are. So there is my angle theta. D is our, so theta equals the angle. D here is going to be the space between the slits. On the diffraction grating. N is my order number. The order is the bright spot number from the central maximum, which is N here equals 0. So that's 1, 2, 3, so on. And we've got my wavelength, which is the wavelength on my laser. And on this particular laser that I've got, then it can tell me what the wavelength of this laser is. And here we can see that if I zoom in, then it's about 650 nanometers. And that is of course plus or minus 10, because this is only a cheap laser rather than an expensive calibrated laser. It was expensive enough, but it's still relatively cheap laser. So if I've got this, then we can try and play around with all sorts of bits and pieces. Sometimes when we've got our diffraction grating, we've got here this, we want the space between the slits, and what we're given here would be lines per millimeter, which means we've actually got to do initial calculation to try and work that out. So we can say, to work that out, that D is going to equal 1 times 10 to the minus 3 over the number per millimeter. And so we can manage to work out D, and I can manage to work out then from my equation, which is n lambda d sine theta, we can work out all the things that we need to if we don't know one of these. So I can work out my order, my wavelength, all sorts of things, and gives rise to lots of interesting experiments that you can actually have a go at doing so. We could possibly even see if the diffraction grating is correct when it says there are 100 lines or whatever. When we look at something like a CD, you have a CD in your hand and you can move it slightly, you can find that we can get this sort of spectrum produced because it itself is a diffraction grating. It's got lots of tiny grooves on it which you can't see, but they're that fine that we can sort of get light to sort of pick it up. Alright, so that's our first idea, looking at diffraction. I'm just looking at how we're doing for time, but we'll see how we can go. I want to now go on and look at polarizing light and see what we can do with this. So let's go over and look at the experiment. Right, Paul's just going to zoom out. Right, okay, so what we've got is a slightly different experiment this time. We've got our polarizing filters, and I've got two polarizing filters. We're going to try a relatively simple experiment here so that you can see what's going on. What I'm going to do is I'm going to try and put up a polarizing filter such that you can see it. And to help this, we're going to put some sort of light behind this. So let's put my light behind this. And this requires just a little bit of fiddling around. I'm going to take the light down enough, more down. Right, okay. Now I'm going to raise this up so that it virtually covers that light. Right, now what I'm going to do is I've got another polarizing lens. What I'm going to do is I'm just going to hold this one in front there, and I can rotate this one. And as I rotate, we can find that the light goes and we lose all the light from that light. And as I turn it a little bit more, the light becomes fully visible again till it looks the same. I'll just rotate this a bit more until it goes. It's about as good as I can get, but if I pull it up you can see the other light is still there. It's just that this polarizing lens is completely cutting out all the light. Polarizing light, quite interesting. Let's have a look at this.
I'm not sure.
Thank you, Alexa. Now, there is something quite interesting looking at this. I can turn this as much as I like, it's not affecting anything. But there is something interesting when we look at a television. And when I look at a screen, something interesting sometimes happens. Let's try an experiment that I haven't had a go at. So what I'm going to do is I'm just going to flick this up and I'm going to look at my screen. And if I've got my screen and I've got polarized sunglasses on, then it might be that I can't see anything on the screen because the light coming out from my PC is also polarized. Interesting. Sort of, I've seen various students discover this. They come into my lesson, they come in and they've got their shades on, it's warm out, nice and bright outside, typically warm. I don't know why people wear sunglasses in the summer and not the winter. If it's a bright day in the winter you need them just as much. So they come in, summer's day, they look at the screen and go, oh, it's not on. And then they switch the screen on. Still not on. And they switch it on again and they see the little light at the front says the screen is on. They can't see anything. And then they take their sunglasses off and oh, suddenly they can see the screen. Something I find amusing. Let's look at this one and see what's happening. What I've got is I've got light coming from my light source, and this has light waves going in this direction, they've got them going in that direction, in fact they've got them going in every direction. When we put this polarizing filter, it only allows light of a particular orientation to go through. When I take this and put it through another filter, if it's in the same direction, then light will travel through quite happily. But if I had the same setup and this time we've got this filter in a different direction, then we get simply no light. So that's diffraction and polarization. And of course we get partial polarization as well, and this is why wearing these glasses can be really quite good if you're in a car. You get these reflections and you can't see quite well, and you're in your car, you put your sunglasses on and we look much better because we can only see certain directions. Whether we ought to have glasses that you can adjust like this one, so we can actually turn it, and you can probably gather this was homemade by me, then it's a little bit different. Right, our next little experiment I promised that we'd have a look at is interference, and we'll start having a look at this and probably continue next time. Let's go and have a look at some interference. So let's put this experiment away, and we're going to go and have a look at the ripple tank again. Right, okay. We had a little problem with the ripple tank there, but we've got that problem solved. That was because we unplugged it as well as switching it off. Right, okay. So we've got the ripple tank and we've got one hole. What happens if we have more than one hole? And what I'm going to do is I'm going to set up this with now more than one hole. I'm going to set it up with a reasonable gap there, and let's set the motor going. It needs a bit of a kick start. And let's look at the waves that are formed. Just as before, we've got a gap, and in this gap we've got our one wave coming out. In the other gap we've got the other wave coming out, and where they join, these two waves intersect, either the wave is being amplified or it's being got rid of. And if I look down, we can sort of see perhaps some lines going through on this. Let me bring this out a little bit. This is going to make it a little bit easier for Paul to have a look at. So he's going to come around the side. Right, it's going to come around the front. Okay. Bit of manoeuvring of the tripod. Is that better, or should I push it further back? I think it's better forward, isn't it, for you? He shrugs his shoulders at me. Right, so what we can see is the waves coming out, and we've got sort of just about here I can see some lines. You get an artifact of the camera working, and that sort of makes it look like the waves are going sort of inwards rather than outwards. But we can see some places, like here, we've got something happening there, and it's not terribly easy to see, because what we need to do is look at this better by freezing the frame or by using a strobe to have a look at it. And trying to get the camera to work as a strobe seems to be a bit difficult because it's got a rolling shutter and it sort of works at its own sort of speed. And if I change the frequency, if I don't, I'll get Paul to change the frequency. We might get better lines appearing. I can see them at the top of the frame, they're looking a bit better. It'll give the impression they're going in rather than out. And we're getting some rather interesting curving artifacts here. There I can see, that was my piece of metal moving. They tend to sort of vibrate along a little bit. But there we've got some look of interference going on. We've got some sort of lines I can see. Okay, we'll switch that off. So we've got some measure here of interference as we look in waves. Basically, we've got a system that looks something like this. What I've got is I've got two sources of waves. Now, while I'm doing this, Paul's going to set up another experiment for me quickly, and he's going to raise this and put the two dibbers in. Right, so I've got these two sources, and these are...
Play the song I've Got It All.
Alexa, stop. Amazing how useless the machine can be.
Just to confirm, you'd like to hear the
Alexa,
song I've Got It All.
Stop. Don't work with animals, children, or it appears these special machines that I don't want to mention its name in case it takes me too literally. I'm trying to draw these approximately the same. Easy with a compass. Where the two bits of wave hit the two peaks, these are accentuated. So if I've got this wave and it coincides with this wave, then the peaks amplify and we get much bigger waves. Where we have this wave meeting its opposite, then it gets cancelled out. And this we call two-slit interference. Now, Paul's busy setting up the experiment at the moment, and he's trying to put the two dibbers in, taking out the piece of metal instead. And if we now get this to vibrate, Here we've got these working as little circles together, and if we look at the middle bit here much better, we can see the interference. We've got little bright spots or dots. Now we can't freeze these easily. Here, I'll move the wire out of the way for you. But what we can see better, if we can sort of take a snapshot here, we can see where the waves are making larger waves, constructive, or where they are obliterating each other, destructive interference. So putting the two dibbers in shows this much better. Paul's just going to show us what that looks like. Can you just show us the two dibbers in there? And he's just going to set the camera up on those two so you can see what it looks like from on top. There's the two dibbers, and when it's switched on, we can see that they're making their shapes. And you can see the pattern on the surface of the water just as easily. And we can also see this when I go into my pool and I can produce much bigger waves. I am lucky that I've got a much bigger ripple tank that I can do some experiments on, which is a pool which I can try and play and do various other exciting experiments. Yeah, not everyone does experiments in the pool, but it's what I find interesting. So we've got this interference. Now, what would happen if we did this with light? Well, that brings us on to what we're going to do this time next week, when we're going to have a look at Thomas Young's double slit experiment and what that shows us. So thank you for watching. I hope you've learnt something. If you did and you like this, then please remember to subscribe, and I will see you same time, same place next week. Thanks for watching. Bye bye.